Good morning, students. Today we'll be looking at the open-ended questions for your Term 1 practice paper. So let's start. So for the first question, question number 8, Wei-Ming read a book about survival skills and created a setup that is able to purify seawater for drinking as shown below. So right off the top, if you've done enough practice, you should know that this is a water cycle setup, even without reading on. But of course, we need to read on to be certain. So the question then asked, using the concept of the water cycle, how is this setup able to purify seawater into drinking water? Now, so the keywords would be water cycle. So once again, as I always said, for water cycle, there are two processes that drives this process. The first process will be evaporation, and the second process would be condensation. So make sure in your answer you mention this process, right? So how do we then pen this down? So what happens in the actual process is that this part, your seawater, will actually gain heat from your sun, and it will evaporate into warmer water vapor. The warmer water vapor will then touch a cooler surface, which is this plastic film here. Just going to pen that down for you. And then it would lose heat and then condense into tiny water droplets. So this stone helps to weigh your plastic down such that it forms a depression, allowing your water droplets to then roll towards the center, meet each other, form bigger water droplets, causing it to actually drip into this bowl. Alright, so what I've done is to describe to you the whole process. So how would the answer be like if you're going to craft it? So what happens is that seawater gains heat from the sun. So remember I mentioned about gaining heat. You need to actually tell me what is the direction from where to where, and evaporates into water vapor, right? Then, okay, or rather the next step will be warmer water vapor touches the cooler surface of the plastic film, loses heat to it, and condense into water droplets. So this is how you get pure water droplets. Of course, you can then continue to talk about how the water droplets would then roll towards the center, okay, form bigger droplets, and then drip into the bowl of drinking, into the bowl, collecting your drinking water. Alright, moving on. B. He also read that changing the stone to a block of ice of the same size will increase the amount of purified drinking water. So what are some of the keywords here? Block of ice, same size. Okay, increase the amount of purified drinking water collected. okay, in the same amount of time. So for this, okay, now how do you think that this would happen? Okay, now, so let's think about it. What is the difference between your stone and a block of ice? The difference between these two would be that your block of ice has a much lower temperature, right? So this lowering of temperature would cause your cooler surface to be even lower in temperature. So think about it. In which part of the water cycle does a cooler surface actually involve? And the answer would be your condensation process. Because it is during your condensation process that your water vapor needs to lose heat to the cooler surface. So when you think about it, heat always get transferred from a region of higher temperature to a region of lower temperature, right? So I'm just going to erase this so I have a bit more space. So think about it. If you have a cooler region over here, your warmer water vapor, which is over here, when it touches the surface, heat will be lost from your warmer water vapor to your cooler surface at a faster rate. So because now heat is being transferred away from your water vapor to your cooler surface at a faster rate, it also means that condensation would happen at a faster rate. So therefore, you be able to get more water droplets at a faster rate, resulting in you being able to collect more water droplets, increasing the amount of drinking water. So how do we then convert that into written form? Okay, so we can say that water vapor okay, or maybe the first thing we should do is, sorry, let me just change that. Okay, so what we need to first say would be that the block of ice decreases, or rather makes, the plastic film cooler or colder. This allows the water vapor or warmer water vapor to lose heat to the cooler surface. You can bracket it and let the examiner know that it is the plastic film you're talking about. Faster and condense into water droplets at a faster rate. Resulting in more water being purified. So what are some of the key ideas here is that you have to tell me that it makes your plastic film cooler than what it was before. It is also important to tell me that the heat is being lost at a faster rate and condensation happens at a faster rate, right? Because the question is talking about how it increases the amount of purified water. Alright, moving on to 8C. Other than replacing the stone with a block of ice, okay, make sure you got that part. State another way to increase the amount of purified drinking water collected in the same amount of time. So basically, when you replace the stone with a block of ice, you are actually trying to increase the rate of condensation. So now the question is really asking you, how do you then increase the water cycle by increasing rate of evaporation instead of condensation? So remember, there are two processes that drives the water cycle, right? So we've talked about condensation in B. So now the question wants you to talk about evaporation in C. So when you talk about evaporation, remember, there are basically there is basically you can use WET to help you. Okay, so you have WET. So what's WET? Once again, remember, these are factors affecting rate of evaporation. So you have W for your wind, E for exposed surface area, and T for temperature. So we must always remember that an increase in any one of these factors will result in an increase in rate of evaporation. Okay, so during the exam, you can write this down to help you. So any one of these factors, if you talk about it, will gain you the marks. So remember, this is talking about a method, so you must tell me how. So I'm just going to talk, have two ways. The first one would be to use a smaller bowl to increase the exposed surface area of the seawater. Now, how does using a smaller bowl help with that? So if we go back to our diagram, if we have a smaller bowl, it also means that the exposed area is actually more. Do you realize that? So that is one way we can talk about it. Okay, so that is on increasing the exposed surface area. Another one that we can talk about would be to increase the temperature of the water by adding some sort of a heat source. Now, sometimes when we decide what would be the most plausible answer, we have to take a look at the feasibility of our solution. So while, yes, I did say that increasing wind will actually increase the rate of evaporation, it is quite unlikely that you'll be able to find a fan when you're trying to survive, right? He's in survival mode. And you will have to put the fan inside the setup such that the wind blows at the inside the setups. Alright, and what will happen is that this will increase the rate of evaporation of the seawater. So this is not very likely. You're talking about a heat source. You could put an additional heat source at the bottom, right? But it would be quite difficult when you're trying to in survival mode, because in order for that to happen, you would have to first find a container that is heat proof and you're able to put the whole setup under the fire. So the most plausible answer in this case would actually be just to use a smaller bowl. to increase the surface area. Alright? Though theoretically, any one of the answers related to the 3 factors would have gained you the marks. Alright, moving on. Question 9. Okay. Miss Ong took out her cooling face spray bottle from her bag on a hot day. When she sprayed water on her face, mist came out of her bottle and tiny water droplets came into contact with her skin. She felt cooler after that. Explain why Miss Ong's face felt cooler after she sprayed some water on it. Now, first things first, this is actually a very common question. Now, what are some of the key ideas here? They said that water is being sprayed on her face, a mist came out, tiny water droplets came into contact with her skin, and she felt cooler. So the fact that she felt cooler here tells me that heat is being lost from her skin, right? Only then will you be able to feel cooler. Now, then the next question that I want to ask myself is, where is this heat being lost? So remember, heat is always being transferred from a region of higher temperature to a region of lower temperature. So when you think about it, what came into contact? The tiny water droplets, right? So your heat must have been lost to your tiny water droplets. Okay? And what happens is that these tiny water droplets would then evaporate as they gain heat. Okay? So remember, in evaporation, you will need heat, correct? So this heat that was gained by your water droplets from her skin would cause your water droplets to evaporate. And as your water droplets evaporates, the heat will be drawn away. So how do we then translate this into a written form? Right, so when the cooler tiny water droplets came into contact with her skin, her warmer skin, remember we talk about warmer and cooler surfaces, loses heat to the water droplets, allowing or causing the water droplets to evaporate. Right, so what are some of the key ideas? So make sure you have the cooler, okay, tiny droplets. It has to come into contact with her warmer skin, because if there's a cooler region, there must be a warmer region. The skin would then lose heat to where? To your water droplets. And what does this heat gain causes? It causes your water droplets to evaporate. Okay, so these are the questions. Okay. Now, next question. Some coffee shops in Singapore are equipped with a mist fan. So this is a very common question again, to keep their customers cool during warm weather. Why is using the mist fan able to keep us cooler compared to the cooling face spray? Okay, explain your answer in terms of evaporation. Very good. Okay, so ask yourself this question. What is the difference between these two setups? You will notice that in both setups, they include tiny water droplets. Now, why is this the case? Because it's stated here that we have this tiny mist, right? A mist fan. So the mist fan is equivalent to your tiny water droplets. So with this, we know that this is the common factor between these two activity. Both have tiny water droplets. Now the difference over here is that your fan would produce wind, right? So when you think about it, they give us a very big hint. They wanted us to talk about how it keeps us cooler in terms of evaporation. Now, remember previously I talked about how when your water droplets evaporates, it removes the heat because it uses the heat to evaporate. So when you think about it, a faster rate of evaporation would so-called it's sort of like it means that there is a faster rate of cooling. And when you think about it, both factors win. Okay, what it happens is that it will cause your evaporation to go up, correct? Not both factors. I meant in this case, sorry, I meant to say the wind is actually a factor that increases rate of evaporation. So you remember your WET? So in this case, we're talking about your wind here. So by having this additional wind factor, it will increase the rate of evaporation so that more water droplets can then evaporate. Okay? Which then allows the water droplets from your fan to gain heat. So how do we then translate this into a written form? Okay, let me just pen that down for you. Okay, the wind from the fan increases the rate of evaporation. So that more water droplets from the fan can gain heat our skin as they evaporate. Alright, so this question is really another question to talk about factors affecting rate of evaporation, focusing on wind. Alright, question 10. Prakash placed 500 ml of water into 3 different containers, STU, ST, and U, and put the containers in the same location. The graph below shows the result of his experiment after 1 hour. Fill in the boxes below with the letters ST and W to match the results to the corresponding containers. So right off the top, this should look very familiar to you, and you should recognize it straight away. It's an experiment that's got to do with factors affecting rate of evaporation. And in this case, we're looking at your WET again, exposed surface area, right? Okay. So when you look at it, you need to recall for exposed surface area, the larger the exposed area, the faster the rate of evaporation. So when your water gets evaporated at a faster rate, it also means that the amount of water remaining should be lesser, or the least in this case. Now, for this kind of question, right, it's also very important to note how many setups there are. So in this case, there are 3 setups. So when you use when you're talking about superlatives here, you have to use the word least, most, and then after that, the one in the middle will be the in-between one. Okay, we can just leave that out, because since you did talk about which container having the least amount of water and which container having the most amount of water, it is assumed that then the container that is not mentioned is the one that is in between. You can do that, but obviously if you want to be more clear, you can say that container T has has the amount of water remaining that is more than S but less than U. You can do that, up to you. Alright, so right off the top, we can already see that container S has the largest amount of exposed surface area as compared to the rest of it, rest of the setup. So therefore, rate of evaporation will be highest. It will have the least amount of water left. So therefore, when you read a graph, make sure you are sure of what it stands for. So on the y-axis here, it stands for total volume of water. So once again, the one with the least, we did say it is going to be S. And then the one with the most is going to be my U. And the one that's in between is my T. So what's the change variable? Okay, so whenever you look at an experiment setup, it's always good to identify what exactly is the change variable and the measured variable. The change variable is basically what you are investigating, the factor that you're investigating, or what exactly you want to see that is different, or what you've changed. So in this case, it is very straightforward. It says here 3 different containers. But obviously you cannot say that it's the 3 different containers. If you take a look at the 3 different containers to see what exactly is different about them. And in this case, you will realize that it's the exposed surface area that is different about these 3 different containers. You need to be specific about it. Okay? And then usually with change variable, you have another very important variable called your measured variable. What are you measuring? So in this case, what the person wants to find out is actually rate of evaporation, right? But you cannot really measure rate of evaporation. You can use a proxy. A proxy means you use something else that you can measure, but you use that to justify the factor. So in this case would be the amount of water left. Okay? This is your measured variable at the end of the experiment. So the lesser the amount of water, that is what you can measure, means that the faster rate of evaporation. Okay? So what is the change variable in this experiment? It will be the exposed surface area of water. Alright, moving on. Next question. After a heavy rain, large puddles of water were left on the basketball court. For their safety, the student had to dry the ground of basketball court before playing. In order to quickly dry the ground, Prakash and his friends spread out large puddles of water using a floor squeegee. How would spreading out the puddles of water allow Prakash to quickly dry the ground of the basketball court? Now, when you think about it, basically what they're trying to ask you to do is you want to quickly dry, right? You want to actually increase rate of evaporation, right? That's about it. That's all the goal of this whole using the squeegee thing is to increase rate of evaporation, right? Because you want to dry the court. So right off the bat, when I'm doing this question, I will think of my WET, factors affecting rate of evaporation. So an increase in any one of these would actually help me increase the rate of evaporation. So then I'm supposed to think, how does using a squeegee, okay, which spread out the large puddles of water, okay, which factor is it actually increasing? And my answer in this case would be my exposed surface area, right? Because when you spread it out, it becomes thinner and it occupies a larger surface area. This would then increase rate of evaporation, allowing the cord to dry faster. Another tip of the day would be that when you are doing questions, usually the first part of the question is a giveaway, more or less, if you get it right. And the second part of question is related to the first part. So when you take a look at it, the application question, which is on using the squeegee to increase the exposed surface area, is sort of related to question A, whereby they want you to realize that a larger exposed surface area will result in a higher rate of evaporation. So using that, you can actually help you craft your answer. All right, so how would your answer look like? So spreading the water puddle increases the exposed surface area of the puddle. This increases the rate of evaporation of the water, resulting in the ground drying faster. Now, it is very important that you remember not just to include the key point, but to use superlatives such as increases, okay? Increases faster. Because whether or not you do this step of spreading out the water, your water puddles will eventually evaporate. However, by doing so, you will shorten the time needed and increase through the increased rate of evaporation. Okay, question 11. Ray Earn poured 500 ml of water into cup W. Next, she put 200 cm cube of ice into each cup. The ice in cup W is a block, while the ice in cup X are smaller. After 5 minutes, Ray Earn noticed water droplets forming on the outer surface of both. Alright? So for this, in this case, we have to actually take a look at what is the difference. Right? So remember, this is like a bit of an experiment. So there is always a change variable. So when we take a look at it, the change variable would be that the ice in cup W is a block, but in cup X is smaller cubes, right? So this is actually the change variable. Now, then after that, they asked you how water droplets formed on the outer surface of a cup. Okay, so remember, I said earlier in many of my explanation, when you see water droplets forming on a surface, it means that condensation has happened, as well as the part where you find your water droplets, that is where you have your cooler surface. So if there's a cooler surface and you see water droplets, condensation has actually happened. So in order for condensation to happen, you need a source of warmer water vapor, you would also need a cooler surface, right? For your water, for your warmer water vapor to lose heat too. So once you've identified these two, you will then be able to explain how the water droplets come about. So we already know where is our cooler surface thanks to our water droplets that will identify the cooler surface for us. The next thing would be to identify where is the source of the warmer water vapor. So the source of warmer water vapor would be your surrounding air, right? So in your surrounding air, you do have warmer water vapor because air is a mixture, right? So the water vapor would touch the cooler surface of your cup, resulting it to actually condense, lose heat and condense. So let's pen that down. So warmer water vapor from the surrounding came into contact, or we can say touches. Let's change this. Touches the cooler surface of the cup, loses heat and condense into water droplets. So by now you should be very clear about the process that involves condensation. So firstly, there must be a warmer water vapor touching a cooler surface, losing heat and then condensing. That's about it. Alright, next. Without using a thermometer, Ray En observed the two cups and concluded that the water in the cup is colder than the water in cup W. How did she arrive at her conclusion? So, remember, these are your two change variable, right? One is a block and one is smaller ice cubes. So because of the difference in surface area, your cup X, the smaller ice cube has a smaller surface area, heat can actually be gained by your ice cube at a faster rate, which means that the water that it is in, the water surrounding the ice cube, is able to lose heat to the ice cube at a faster rate, causing it to melt faster. When this happens, we know that in terms of temperature, the water in cup X would be lower, or it will decrease at a faster rate as compared to your cup W. So when that happens, it also means that the surface that you have, when you compare these two, okay, the surface over here is a cooler surface due to their lower temperature when you compare these two. So what happens is that with a lower temperature, it will result in a cooler surface. Therefore, it will also result in the condensation process of your water vapor in your surrounding air being faster, resulting in more water droplets. So how did she arrive at a conclusion? She's able to tell by the amount of water droplets outside the cups, whereby cup X has more water droplets. Okay, so there were more water droplets on the outer surface of cup X. Alright, and that's how she did it. Okay, based on the concept of heat transfer, explain why the water in cup X is colder than the water in cup W. So this is exactly what I've explained earlier. It's due to the fact that the ice cubes are smaller, so there's more surface area for your ice cube to gain heat from your water. So what will happen is that because heat is being lost at a faster rate to your ice cube, your water will actually decrease at a faster rate. Okay, so here is really talking about exposed surface area. So how do we then translate that into your answer? Okay, the exposed surface area of the ice cubes in X or in cup X is greater. Make sure you use superlative and comparison words than the ice cubes in, actually it's not even ice cube, it's ice block, just to be sure, right? So ice block in cup W. So the water in cup X loses heat to the ice cubes in ice cubes faster than the water in cup W. Alright, so this would then result in the water in cup X being colder than cup W. Okay, very straightforward. Alright, question 12. Maya conducted an experiment as shown below. She put the same mass of ice in two identical beakers. She measured the mass of the ice that melted at regular intervals. So what this means is that she just took the measurements at regular timing. So what is the aim of Maya's experiment? So basically for this, right, let's take a look. Okay. Now, when you take a look at experiments, there are two important things to take note of: your measured variable and your change variable. So your change variable is basically what is different. So in this case, the change variable looks at two different types of ice in terms of their sizes. So in A, we have one whole block, and in B, we have the same mass, but now they are in smaller pieces. So the difference between here is actually talking about your exposed surface area of ice, right? So this is your change variable. Now what is she measuring? So it's really very clear indeed. She's measuring the mass of ice that melted at regular intervals. So what she's looking at is the rate at which the ice melts. So when you put the two together, whereby the change variable is your exposed surface area of ice and the rate of melting, she wants to know basically if exposed surface of ice affects the rate of melting. Okay, so what is her aim? To find out if the amount of exposed surface area of ice affects the rate of melting. Okay. Then the next question asks you which beaker will all the ice melt completely first. So another very straightforward question. If you recall in the previous question, the same thing over here. Answer will be beaker B. Why? Because the ice cubes, they have a larger exposed surface area as compared to the ice cube in beaker A. So therefore, heat will be able to be lost from the surrounding to the ice cube at a faster rate, or rather the ice cube will gain heat at a faster rate, therefore allowing it to melt faster. So let's translate that into a written form. Okay, the ice in beaker 2. And why is that so? Okay, the ice in beaker 2 has a greater exposed surface area than the ice in beaker 1. So it gained heat faster from the surrounding than the ice in beaker A. Sorry, this is beaker A and B, right? Okay, I just realized that. Let me just change this part here. So this is beaker B, okay, to make it more consistent. Okay. Allowing it to melt faster. All right. C. Question C. One day after shower, Maya tied her wet hair in a bun. Okay, Maya's mother suggested that she let her hair down so it would dry faster. Explain why her mother's suggestion will help her hair dry faster. So once again, remember, I always told you that usually the questions are related to the same concept that's being tested. So in this case, if you take a look at these two, the second one actually has more increased surface area, has a greater surface exposed surface area as compared to if she puts it in a bun. So when there is a greater surface area, then your evaporation rate will increase, because apparently you want her to dry, right? Dry equals to increased rate of evaporation. So how do you increase rate of evaporation? Any of the three factors, WET. So obviously the difference between these two is increase in exposed surface area. So with that, your hair will actually dry faster, because now your the water in the wet hair will have a greater exposed surface area to gain heat faster and therefore evaporate faster. All right. So let's translate that into your written answer. Okay, so when the hair is down, there is a larger exposed surface area. So the rate of evaporation is higher. Right? And that will allow her hair to dry faster. D. Other than using a towel, suggest another method Maya could dry her hair faster. Okay. So in this case, remember WET. Another one we could use would be to use a hair dryer. Now your hair dryer gives you two factors. The first is increase in wind speed. The second would be increase in temperature. And we know from our prior knowledge that these two factors will help to increase rate of evaporation. Alright, moving on to the last question. Mike filled a jar with some water at a temperature of 80 degrees. He placed an ice cube into it as shown in the diagram below. Would the temperature of the water in the jar after 5 minutes be higher than, same as, or lower than 80 degrees? So, this is actually a question on heat transfer. So with heat transfer, we must know that heat always goes from a region of lower temperature to a region of higher temperature. So in this case, your ice cube, okay, definitely has to be below 0 degrees Celsius. Okay, so I'm going to say that when it first drop it in is, let's just say minus 8 degrees Celsius. This is 80 degrees Celsius. So your water is obviously of a higher temperature. So what happened is that heat will be lost from the water to your ice cube, causing it to melt. And when that happens, your temperature of the water will start to decrease. So if it's at 80, since it's decreasing, it should be less than 80. Okay, so that is actually my explanation. Now we just need to translate the explanation to our written answer. So the answer would be, it would be, or it will be lower than 80 degrees Celsius. Why? Because the water, which is your higher temperature, would lose heat to the ice cube, which is your lower temperature. Now, additionally, your water will also lose heat to the surrounding, all right? Just so you know. Now, next question. Mike placed 4 similar ice cubes in 4 jars, K, L, M, and N. Alright, so this is N, I'm going to fill that in. The jars were of a similar size but made of different materials. Okay, so this is my change variable. He left the jar on the table in the living room. He recorded the time for the ice to melt completely. So we know that he's recording something. So this is our measured variable. And plotted the readings in a graph as shown. Now, then the question goes on to ask you, which material is most suitable to make an ice cream container so the ice cream will not melt so quickly? So one look at this, and I know that this question has got to do with So first thing, always think of the concept, right? It's got to do with poor conductors or conductors of heat, right? So you want to have a poor conductor of heat specifically in this case because you want to prevent your ice cream from melting so quickly. So in this experiment, you can think of your ice cube as your ice cream. So when you take a look at your data, obviously M seems to be the best answer because your M took the longest amount of time as compared to the rest of the materials for your ice to completely melt, since your ice is likened to your ice cream. Now, why is that so? So probably because they're talking about material, M is probably the poorest conductor of heat. So remember, in a poor conductor of heat, it basically transfers rate at a slower rate. So that is something that I'd like you to pen down and remember. So poorer conductors of heat transfers heat at a slower rate. So it doesn't allow heat to pass through it quickly, or the rate of transfer of heat is at a slower rate. So when you think about it, if I'm going to zoom in to explain this, so because it is a poor conductor of heat, so remember between this region and this region, the outside region is of a higher temperature. Okay, so heat is supposed to be transferred from here to here. But because we have this region here that is of a poor conductor of heat, this rate of heat transfer will be slowed down. So therefore, your ice cream, or your ice in this case, will not be able to gain heat so quickly and melt away. So let's translate that into our written answer. So M is the answer. M as the ice in M takes the longest time to melt. This suggests that M is made of the poorest conductor of heat. Okay, as compared to K, L, and N. You can go on to elaborate further if you want, which is that therefore the ice cream will gain heat the slowest, slowing down the meltdown process. Okay, or sorry, can I just change the last part? I think it's better to say slowing down the melting process. Alright, and there you have it. Okay, just make sure you use the right superlatives because there are more than one. You have to use poorest, okay, and slowest. Alright, thank you so much. Please take your time, review the video again as many times as you need.